Hello and welcome back to Let's Code Physics. Last time we were successfully able to implement a double integral, that's these two loops you have here over x prime and y primed, to determine the electric potential created by some charged surface. So our charged surface in this case is a square because we've got x prime and y prime, each running from -1 to 1. If I wanted to stretch this out into a rectangle, I could just change one of those dimensions. We will play around with the shapes a little bit later in this series. First, I want to get more of the machinery built, because right now our integrator is only returning the potential at one point, right? So we're integrating over x prime and y prime, but we're evaluating the electric potential at some point x, y, outside of the charged surface. We don't really want to evaluate it inside the charged surface because then we would be dividing by 0. When we go to do this scriptar calculation, at some point we would have x equal to x prime and y equal to y prime during the integration, and that is not a good thing to be dividing by. And so, like I said, we'll play around with the shapes a little bit later. What we're going to focus on today is generating some graphs, because while it's handy to get the potential at a single point, that doesn't really tell you a whole lot, especially since the absolute value of a potential doesn't matter all that much. It's the change in potential from one point to another that matters in terms of physical applications. So we're going to set up another loop. So we've already got two loops here to do the integration. We're now going to set up a loop to move our field point. So as a visual reminder, we have our charged surface somewhere in the middle here, and we're evaluating at a field point out here, x comma y. And so what we'd like to do is iterate, not integrate, but iterate over various points for this field point. And for today, we're just going to change the x value. So we're going to get graphs of the potential versus x for a fixed value of y. So we'll start out at some x value, then we'll move out a little bit more, out a little bit more, and then we'll be able to graph the potential versus the x coordinate. And since we've got an isometric square, that's going to be it'll be the same thing as if we were varying y. So let's see. So we need to start a loop for x. We need to think about what needs to change each time we loop to a different value of x. The integration bounds are not going to change. It's still the same charged thing. The number of integration points is not going to change, so the step sizes are not going to change. But we'll have a different potential value for each one, so I need to have the potential value in this. And let's actually have our y value stay constant, so let's leave that outside of the loop. So we'll say for x, equal to, I need an x-min, a dx, and an x-max, not to be confused with my x prime min and x prime max and dx primed. So now that I've got those two set up, I don't need these two, and this end is going to have to go all the way at the end down here. And now here's a handy trick I learned in Scilab. When you need to update all of your indentations to keep track of your loops, select it all and press Ctrl-I, and it will indent everything for you. Also a good way to make sure that you've got enough ends set up, aside from the neat highlighting trick there. Let's see, so we're keeping y fixed at 2, so I need an an x-min and an x-max. So let's see here, we started at x equal to 0. And let's see, so we have and that gave us a 0 value because of our symmetric charge density here. Let's actually change this back to a constant for right now. We'll go back to it being linearly distributed across x in just a moment. And then x max, let's go out pretty far. Let's go all the way out to 100. So the scale for the problem is sort of being set by our charged surface. So our charged surface has a width of 2, it's going from -1 to 1. And so going from 0 to 100 is getting significantly far away from the charged surface. So that'll be interesting to see. And then for dx, let's do the same type of trick we used up here with a number of points. So we'll call this now x max and x min, and we'll call this, instead of number of integration points, number of graph points. Cool. And so I need to define a number of graph points. It's always best to go with a relatively large number. Let's go with 200. So in other words, this loop over x here is going to go 200 times, because it's going to go from x min to x max instead of dx. Actually, it'll either be 200 or 201, because I think it has to count the endpoints. But either way, it's the order of 200. So this is going to loop 200 times. Within each of those loops, it's going to loop another 200 times another 200 times. So this is actually going to take a little bit. So I'll probably end up cutting what we run here. Just for sanity's sake, I'm going to, just for now, have this thing display the value of x so that we can make sure it is progressing nicely. I think that's all that we need. So let's run this thing and check out the answer here. Okay, cool. It is progressing along, although I made a mistake. I have not yet finished the actual graphing, because what it's doing right now is it's calculating the potential at each of those points, but then it's writing it over each time for the value of potential there. So I need to be able to store that in order to graph it. So here's how we're going to do that. For saving the results, let's set up a new, let's set up a calculation up here. So let's begin arrays for storing data. So the way you graph in Scilab is you create an array, call it, for example, potential array. And then you have to graph potential array versus another array, call it X array. I guess I should capitalize that A to be consistent. And the calling it an array just reminds me this is the thing we're storing it as an array. No, I do not want to restart my computer right now. Thank you very much. I believe I can set this up as initially empty. And then what you do to add to it, so at this point we're done calculating the potential. We've gone over, let's see, oh sorry, at this point we're done calculating the potential because this is the end of the integral. Actually, let's make a little note to ourselves. Begin integration, and then end integration. Cool. And so what I need, oops, not that thing, I need potential array equal to, and then the way you set this up is you just tell it whatever you had previously in potential array, and now add the value potential. And so what it's doing is it's basically adding this value to the list of values for potential array there. And then I need to do the same thing with x array, comma, the value of x. Cool. I could have gone ahead and set up the x array and then looped over the x values, but this I think will make more sense later on when we need to do irregular shapes. I believe that's the way I set that up. If not, I'll probably just cut this part. Plot, then we say x array, comma, potential array. All right, let's see if we get any error messages from this thing. All right, I've not gotten any error messages, so let's assume that is marching along just fine. So I will cut here and we'll take a look at the results that we get. And here we are coming up on the end. I decided to put the display X back in there after all. And now we get to see the graph together. Okay, cool. So let's take a look at some of the general features. You would expect the potential to die off as you get farther away, right? So the effects of charge or mass or whatever the source is tend to decrease the farther away you get, right? Things don't get stronger just because you get farther away from them. Springs behave that way until, of course, you break them. So that only works as like a local approximation. But, you know, fields type things tend to get weaker as you get farther away. But what's interesting is that there's a little bit of a maximum, or not a maximum. There's a little bit of a concave down structure right here. So that's interesting to me. Let's see. So we were starting at x equals 0, right? Right. Oh yeah. And this is the constant amount, not the linear amount here, because otherwise we'd expect that to be 0. So we'll try that one next. But that's interesting. That would be something interesting to probe. We could go negative, but because this thing is symmetric left and right, you basically take this image and copy it and flip it around. Let me see if I... Oops, no. That is a zoom. That is not... That is a rotate. That is not a zoom. This is where I... Original view? No. Tools. 2D, 3D rotation. Almost. There we go. I was trying to zoom in on that spot. Fortunately, all the data is still there, so we'll just do plot x-array, comma, potential array. There we go. All right, let's try that again. Now, how do I do the zoom in? I think I use this thing. Yes. So I might be interested in zooming in on that top corner there. Oh, and of course, I've only got a few data points there. Let's run this again, and let's go from like 0 to 2 to get an idea of what that maximum looks like, because that's kind of interesting to me. Actually, let's even... So what I can do now is, now that I've got a spot that I'm interested in, I can go from -2 to 2, get an idea of what that maximum looks like. Let's see. Do I want 200 data points? I don't think I need 200 data points. I think I can go with, say, 50 for that range. So let's run that, see what our maximum looks like. Need to exit this. There we go. Okay, cool. So this is what our maximum looks like. That looks darn near parabolic. So another thing that might be interesting to find would be the inflection point, right? Because this part is concave down. The next part, if we continue out, goes concave up because it's opening upward. So somewhere in between there has to be an inflection point where the concavity changes. So that's interesting. Rather than hunt down that point, though, I'd like to take a look at this other case that we looked at last time, where we have a linear charge distribution in x primed. So that's the case where we've got negative charges on one side, positive charges on the other, and the charges get stronger the farther away you go. So you got a strong negative charge over here, strong positive charge over here, 0 charge in the middle. What we saw is that if you evaluate the points, if you evaluate the field at a symmetric point up here, you'll get 0. And so this thing's going to have to grow and then diminish. So we should get a maximum off to the side here. This time let's go, I don't think we need to go all the way out to 100. Let's go from -10 to 10. And 50 data points. Let's go with 100 data points. Just to see what this thing does. So let's run this. All right, we're moving from -10 to 10. I will see you when we reach 10. Okay, cool. Let's see. We did get what we expected. So at 0, we have 0 potential. Now, again, that's arbitrary because you get to pick where the offset is. But that means the shape of the graph is going to be the same. It's just going to be, shifted up or down. We do get a maximum out here somewhere. We get a minimum down here somewhere. Interestingly enough, the max and the min are not at -1 and 1, which would be the midpoint. They're shifted to outward just a little bit, but they're also not at -2 and 2. I'm wondering, is that a maximum at square root of 2? Because that would be really interesting. We had square root of 2 show up in our pendulum video. Let's see here. Let's zoom in try to take a look. Now it's going to become jagged when I zoom in, but it gives me an idea of where to look. Let's see, square root of 2, 1.414. That minimum could be somewhere in there. Let's try going between negative 1.5 and negative 1. So let's go from negative 1.5 to negative 1. So this is the type of fun you get to have with these routines where it's doing all of the math for you, is you can look and find these neat features. It's like doing an experiment, but you don't have to buy a whole bunch of equipment. You just need software. So I got halfway through that one, realized I typed in a positive 1, not a negative 1. We don't need 100 data points for that region. Let's just go with a nice 50. There we go. All right, let's try that again. Here we go. 5, 4, 3, 2, 1. Happy new graph. Ooh, okay. No, that minimum is not at square root of 2, because square root of 2 is 1.414. That would be over here. So that is somewhere out here. It's between negative 1.28 and negative 1.3. So the other one, it's symmetric. So the maximum is going to be somewhere between 1.28 and 1.3. Is there a special number in there? Is there a special number like square root of 3 or something? Square root of 3 is 1.7. No. Oh, you know what though? It might be a bit arbitrary since I am up 2 in the y direction. I wonder how that moves if I change my y value. So I'm going to leave this graph open, so this will overlay the next graph for y equals 2.5. Let's run the same calculation, but this time we'll have a different y value because that's probably going to affect the location of the maximum along the x direction. Okay, we have reached negative 1. Our code has concluded. It did replace the previous graph. Well, the previous minimum was somewhere over here. That minimum has moved rather far to the right now. So I guess what I should do is, I suppose what I need to do is have this run the full range that I was looking at. We did negative 10 to 10 last time. There we go, to get the full picture. So let's do this. Let's have it run with 2, and then I think the way you keep this is say hold on to keep the graph on there. And then, so we'll run it once with 2. We'll run it once with y equal to 2.5. We'll see how much the location of the min and max change. Okay, coming back out here. Okay, good. It kept them both. All right. So the minimum, okay, so this is the new graph right here, the one with the less extreme max and min. That makes sense because with y being equal to 2.5, we're now farther away from the source than we were before. And what we get is that the location of the max and min has spread out a little bit. Which I think makes sense because as you get farther away, you would expect this thing to flatten out. And so as this thing flattens out, the bumps are getting less extreme and they're moving outward a bit. What this is motivating us to do is to create a 3D graph, one where we have an x-axis, a y-axis, and then an axis for the potential. We're going to do that in another couple videos. What I want to do before we move on to that, next time what I'd like to do is I'd like to compare these against the results of what's called a multipole expansion. So we'll get into comparing these graphs with the way they're quote-unquote supposed to be according to when you do a Taylor series expansion on the potential. But I think that's good enough for today. This is a lot of fun to play around with, so feel free to download this code from the link in the description below. change up this charge density, and share with us your pictures of the graphs that you get, because you can get some pretty neat stuff with this integration code. So thank you so much for watching. I will see you next time. Bye bye.